Okay, super. So we were looking at some ways of automating proofs, right? Very tedious proofs by using very rich programming, meta programming ability in Coq. We won't use it that much in this course, but it is useful to be aware, right? So I think, um, yeah, I think if you were to use Coq at some point, you should be aware that Coq is not just useful for like very tedious proofs, but you can also use Coq's tactic system to simplify proofs. So here is one other thing that we will, this is the last example that we'll go through in basic syntax and move on to the next lecture. So yeah, so what are we saying here? So we are essentially saying that the commuting function that commutes the terms, right? Plus it commutes and times it commutes. Um, and if you apply constant fold on an expression and then commute it, it's the same as first commuting and then applying constant fold. This is, I mean, intuitively, we believe that this is true. But because of this construction, because there are so many cases within constant fold, this gets very, very tedious. So here is a very short proof, right? But let me tell you how we sort of arrive at this proof, right? So if you do induct, I mean, the idea is to solve this by induction on E, right? We sort of look at the terms, get the induction hypothesis for the subterms, and then we try to prove it. So let's induct on E and simplify each of the terms. Okay, and then you see that this way. So you have a const n equals constant here. This goes through with equality, right? This is just equality is reflexive, so that goes through. Second one also is of that shape, right? So one thing we can do is we can try to start off by saying, okay, is it possible that all of these goals go through with equality? So we can try something like this. So you start um, repeating match goal with, sorry, repeat is a tactic which repeats the tactic. Repeat is a tactical, sorry. And then what you do is we want to see what we want to do. Actually, let's try this, right? Let's first um, before we move on to this, let's just try the simple one. So for each of the goals, apply equality. So this doesn't work, right? So it says, oh, tactic failure congruence failed because equality is not applicable for all of the subgoals to prove it. So equality will hard fail, right? Hard failure is like, oh, I just can't prove it, so I'm going to indicate a failure. You can make this a soft failure with try tactic. So if you try equality, the first two would have gone, right? But there are two more sub goals, one for the times and one for um, the plus, right? So you scroll, I mean, this is a huge term, right? If you sort of scroll down here, this is times, right? And then there is one other for plus as well. This is plus, I believe. Yeah, plus is here. So as we saw earlier in the same lecture, the way to approach these goals is to analyze each of the cases here, each of the patterns here. So what we did is we sort of said, okay, case analyze this term so that you specialize for each of these subcases and then continue. And for that, we used this sort of a tactic, right? So let's copy this and paste this, and then I will tell you what it does. So, okay. So what this is saying is, oh, I see this pattern where I sort of have these cases. I want to do case analysis. Maybe simplification will let all of the cases pass, right? Let's try that. So if you, so I mean, this is the same as what I did earlier. So what is saying is, if you have a subterm which is a match, and you have a thing which is E between the match with, do case analysis on E, simplify the term, and then try with the equality, right? So let's try that. This takes a while, right? So it actually takes a few minutes, sorry, few seconds, which tens of seconds, right? Let's wait for a bit. So Coq is actually destructing the terms and working with the terms, expanding it, trying to prove it using equality. A lot of times it will fail, right? But because we have a repeat, it is going down. We have nested pattern matching, so it is sort of going down towards all the cases, and then trying to apply this tactic and trying to prove that it is going to work. Yeah, so this will take a few more minutes. Okay, fine. So what we have here? So we have 12 sub goals. Why didn't this one go through? Right. So why equality does it go through? So it solved many of the goals, but some of them are there. Oh, equality is going through. Okay. So this goes through. Fine. So I don't know why this one got stuck there. But anyway. Okay. Anyway, so let's not analyze that. I want to get to the interesting bits. So, okay, so now let's focus on this particular sub goal, right? So we have 10 other cases to prove, and we have these terms. So let's focus on the first one. So this is how you focus, right? So let's see why we can prove this. So I want to show that the constant term n is equal to the constant term of s of n0 plus n1. And what do I know about n0 and n1? I know that const of 0 equals const of n1, right? And which must mean that 0 equals n1, right? N1 is 0. And what do I know about n0? I know that const of n is const of s of n0, right? So which means that n is n0 plus 1, right? Given that n1 is 0 and n is n0 plus 1, this should be true. Do we agree? We do, right? So it's sort of just looking at the constructor. So we have to take this constructor apart, right? We have to take this constructor apart both in the hypothesis here, right? So that we learn from this fact that n1 is equal to 0, and we also need to change our conclusion in this here in order to convert this into proving n equals s of n0 plus 1, right? There are two things to be done, as we have previously seen for conjunction and disjunction, right? The way you manipulate similar looking terms, when conjunction appears in the hypothesis, we have to use a different tactic from when the conjunction appears in the conclusion, right? Because they mean two different things. So one thing to do here, right? So if you happen to have something like this, where you have a fact, essentially, we have a fact, and what we are trying to do is to learn everything else that is that can be deduced from this fact, right? So if you want to learn from this fact that n1 equals 0, there is a nice tactic in the FRAP library, which is quite powerful. Actually, this is going to be extremely powerful. So one thing it does is when you apply this invert tactic, right, on IHE1, so observe what happens. So, I mean, it has also simplified. So observe that this particular assumption will be gone. But where n1 was here, we have replaced that with 0. So invert is sort of quite powerful, right? We will use invert for a lot of things in the upcoming lectures as well. So the way to sort of look at invert for now is if something is obviously true that you can see in terms of something like the constructors are there and you want to prove something about the parameters, right? Those facts are, if you want to bring out those facts, you use invert. Okay, I applied invert on that. That went through. Here is also one fact, right? We need to also use this. We need to learn the fact that given these two are equal, it must be the case that n equals s of n0. So let's also invert IH E2. right? Now we can see this, right? We can see that S of n0 equals const of S of n0 plus 0, right? So we've arrived at this stage, but we are still not done. So ring tactic will not make it go through, right? Because this is not a pure arithmetic expressions, right? Um, Typically, ring would have solved this, right? Because this is just the S of n0 and S of n0. Um, we know that n0 equals n0 plus 0, and ring tactic will make it go through, except that we have these two constructors that are sort of sitting in front, which is preventing the ring tactic from being applied. And what we need to do is to say, okay, in order to show this, I can show, it is enough to show that n0 equals n0 plus 0, right? And the way you do that is to apply this f equal tactic, right? The way to read this f equal tactic is, if I have, say, uh, f of 5 equals g of 5, right? Then I mean, given that they are the same, then I just need to show that, okay, not f of 5, g of 5. Say f of x equals f of y, right? I know the fact that f of x equals f of y because f acts as a function, right? We know that functions map one to one, right? So if f of x equals f of y, then it must be the case that x equals y, right? So if I need to show f of x equals f of y, it is enough to show that x equals y, right? That is the reasoning that we are using, and that tactic is called f equal. You, in OCaml, constructors are not functions, right? But in Coq, even from the definition of these constructors, you can sort of imagine constructors as functions as well. So every constructor, say something like the constructor, see, the const constructor, right? I can do this, I think. Yeah. So const says, I mean, the type that you get is a function type, right? It says, give me a natural number and I will give you an arithmetic expression. It's sort of constructing that value, but you can also interpret that as a function. So, why am I saying this? So if you look at this step, right, you have like one function, two function, right? F of g of n0 equals f of g of n0 plus 0. So if I need to show that, then because f and g are just functions, right? It is enough to prove that n0 equals n0 plus 0. So f equal tactic is the one that allows you to do that. So if you apply f equal and apply f equal again, you get n0 plus 0, right? And now ring will make it go through. So that has gone through. So the thing is, there were two things that we did, right? We said, oh, anytime we see a constructor, um, anytime we see something like this, right, which is f of 0 equals f of n1, in the assumption, we know for a fact that the arguments must be the same. So for that, we use invert. And anytime in the conclusion, we have a similar looking structure, we need to apply f equal. So there were only two cases. So let's see if these two cases will let the proof to go through, right? For that, here are the two things that I copy over, right? So I've added two more cases to this repeated pattern match. Okay, so I have, what do I have? I have in the set of assumptions, right? This is on the left hand side of tilde, which means it is a set of assumptions. If I have an assumption where I have f of underscore equals f of underscore, I'm just not naming these things because I don't need to. Then do invert on h to learn the fact from that particular hypothesis. In particular, what it says is just drops the f and gives you that fact, right? And then I'm going to try linear arithmetic. Linear arithmetic also works just as the same as ring here. It's fine to use linear arithmetic here. And similarly, if you have a conclusion where you have a similar structure, where you have some f of x equals f of y, then convert that to proving x equals y. For that, we are using f equal. and I'm going to try linear arithmetic, right? So I'm going to keep trying this until I succeed. So that is why I have a repeat here, right? So this is the entire construction, right? So let's see whether this goes through. And the thing that I'm going to try to do is to also time it, right? So what I will do is I have this nice tactical. Again, this is another tactical which just says, um, give me the time of execution of a particular tactic. So far, we've been looking at very small tactics which run very quickly. But as you see, as you will see here, these sort of exploration, right? This sort of um, the way of automatically proving things by applying repeated versions of some tactic and trying it out will take a long time because we are not being very clever about how to prove it. We are just like exploring all the cases and trying to go through. So this might take some time. I'll just show how this works out. So time takes a tactic. So I've combined all of this into a single tactic, right? What are we going to do? We are going to induct, simplify, and then repeatedly apply this goal. If you have a match, we are going to try cases, simplify, try equality. Otherwise, we are going to do these two, right? So invert a hypothesis or apply F equal. So this will take some time, right? So it's going and processing here. So it's sort of doing its work. This will succeed, right? So you can take my word for it. I think it will come back in like 20 seconds. Any questions on what we are doing here? This invert tactic and F equal tactic. So these are new tactics that we've seen here. Questions while it continues processing. No questions? You must have some questions, no? Okay, that ran for 44 seconds, right? And then we have no more subgoals. So essentially, what would have turned out to be a very complicated proof. Actually, not. Let me take that back. Not complicated, right? Very tedious proof where you have to explore each one of the cases, invert it, and then invert the right tactic, and so on. We just used automation, right from the get-go. And what I showed you is how we end up with this automation, right? So you sort of say, oh, I'll try this. And then if not, I'm going to try something else. And I'm going to lift it up and push it into this automation framework. And that is how these sort of complicated tactics are built up, right? And that sort of concludes what I wanted to say about the basic syntax. There is more stuff in the file called basic syntax.b. There are a few more um, like properties that are proved. I recommend you to go through it, right? So they're going to apply the same sort of reasoning that we've done here. Some of it we've already covered in the first 3 lectures. So that's why I'm not covering it here. Have a look at this particular file, right? So this file is called as basic syntax underscore lecture. And that is the original file basic syntax.b. I recommend you to take a look. And I also recommend you to read the FRAP book. So there is a PDF that is available from the FRAP website. It's sort of a compressed form of what is done here. In particular, it doesn't involve any cop, right? But it is sort of written in a nice way to explain some informal reasoning about why something is true and so on. It doesn't actually touch upon the proof, right? And the property, and that is by design. So the whole point of this book is you're not going to do any sort of proofs, even hand wavy proofs on paper. So everything is going to be in code. So it's a nice book. I think it will become more and more useful as you go through the rest of the lectures. But I recommend you to read those chapters. Each lecture will be like 3 or 4 pages. A very easy read, right? So I recommend you to have a look as well. Okay, so that concludes the basic syntax lecture. So the next thing, so what we studied so far is just the syntactic reasoning, right? So we said, oh, we have this language, and we are going to study the properties of the language by looking at the syntax, right? And we've done commutation, constant folding, depth, size, and so on, and we proved some properties on it. But really, when you write programs, right, you write programs to run it and do something useful. In particular, we've not said anything about what is the semantics of executing these programs, right? Here we have a very simple arithmetic expression language, but still you can imagine that if I commute a term, right, and I evaluate it, I will get the same answer as the original term, right? These are properties that you might want to prove, and that is what we are going to see in this next lecture, which is about interpreters. So I have a few slides. These are basically taken from the Frapp book, right? So just to set up the scene so that before diving into the Coq code, right? If we establish the scene, then it becomes a little bit easier. So let's look at what we have here. Okay. So what we are going to do here is write an interpreter, right? And as you've seen in the term language that we had, right? We had the constants, variables, and we had what did we have? We had plus and times. So when you interpret the program, say x plus 1, right? What is the meaning of x plus 1? Right? The meaning of x plus 1 should be apparent only if you have some binding for x, right? If you write a little recursive function that interprets the program and gives you arithmetic expression, natural number as a result, then it better provide bindings for what x is and what y is and what other variables are. And how do you provide the values for variables? You have a map, right? You have a hash map, but we just call it maps here because hashing and everything is irrelevant at this point. So we have a map from the variables to their values, which are just natural numbers, right? So we will use that here. So we will use a special kind of map called finite maps. And I mean, as we go through the lecture, we sort of will come across why this finite map is special. The finite map is special because it allows you to prove properties nicely. So if you have a generalized map, then it becomes a little bit tricky. But finite maps let you prove it. And the other thing that I want to introduce by looking at the slides is the syntax that we use for maps, right? These are standard sort of syntax that you will see in operational semantics throughout this course, as well as when you read programming language papers and descriptions and so on. They sort of use these syntax without even defining, right? So because it is understood that this is what they mean. So just to establish what those syntax means, we are introducing the syntax here. So we are going to introduce maps for mapping variables to values, right? And the map could be empty, right? Which we represent with a black dot, right? So it contains no bindings, essentially. It's an empty map. And if you have a map M, we just write M of K to get the binding for the key K in map. So in our case, the keys are variables. So if I write X here, then if you see the syntax, then you should read it as what is the value of X in this binding, right? The other thing to remember is this is purely functional, right? So we are not going to modify the map. So every time you sort of want to extend a map with a new binding, you just add a new key value pair to the map, right? So you sort of keep expanding the map. And what it does is it shadows the previous binding if it is already there. So here is how you extend the map. So if you think M is a map, then this syntax, what it says is, this is a definition of a new map, right? And this map contains all the bindings in M, and it additionally has a binding for K to V. And the way to read this is, if the binding for K is already in M, then this map, right, shadows the binding for K. So if you look up k in this new map, this whole thing is a value, right? If you look up k in this map, what you get back is just a v, because that you're just shadowing the previous map. And this is known as extension, right? We call it extension of a map. And so those are finite maps. Um, Questions on this finite map definition? We are actually going to see how this works, but this is just syntax, establishing some syntax, right? And here is the semantics of how the map actually works, right? So that's syntax. What about the semantics? Um, if you have a map, so this whole thing, right, starting from here to here is just a map. If you have a map which is extended with k maps to v, and you look up k in that, then the value that you get back is v, because that's the value that is bound last, right? And if you have a map where you have k1 binds to v, and you have a different k, k2, and if k1 is not equal to k2, then what you get back is m of k2, right? You just keep looking further down the map. And of course, the way to read these rules is sort of keep applying these rules recursively, right? And when you have an empty map, it is not defined, right? So the good thing about semantics is you can just leave things as undefined, um, and it's just the way we sort of write these notations. So if you observe that there is no rule for empty map, right? When we write recursion, we sort of have to say, oh, what is the value for the base case? We don't have a base case here. We just say these are the only things that are defined. If you give anything else, it's just undefined, right? So that is what we will go with. And Shashin, here is where if you were to write this as a program, here is where you will use a optional type, right? So you would say that the value that is returned is some v, and if you write a program, you have to handle the case that the map could be empty. And for that, what you will say is, if the map is empty and you look up k, then you return none, right?
So doesn't that kind of violate that first statement over there where it says the empty map with phi as its domain? Because now we have none or something as the domain, wouldn't it?
Domain is, it just says domain is empty, right? And all we are changing is that what is the value that you get back when you look up the map. So m of k says mapping of k in map m. So you have to change this definition, right? M of k, if it returns some v, then v is the mapping of k in m. So that's the definition that you have to change, not this one. This one just says that there are no keys, right?
Okay.
It's empty set.
So I guess that
Uh,
empty map is more of a theoretical concept, and how we interpret it in the program is going to be via an option.
yeah. So it's not just theoretical, right? So you can sort of imagine this to be, you can encode maps in variety of different ways, right? One way to encode
Fair,
map is
fair.
to say assume that I use a list, a um, pair of a key and a value in a list, and the extension is just consing to the head. And when you want to look up in this structure, you first match the head. If the key and the key that you are looking up matches the first key, then you return the value, some value. Otherwise, you keep recursing until you will reach the empty, right? The nil state would be the empty map there, and at that point you return map. Anyway, so that's the relationship there. Okay, so we've defined a map, right? And now what we are going to say is we are going to start with a very simple language, right? And the study of programming languages, right, always starts with defining very small languages and then providing semantics to that. We add like little features, right? We sort of add, okay, I know how something works in the small. Let me just add this one other feature, which is like the feature that I want to study. Let me see whether I can show obvious things or non-obvious things about this additional feature. The thing that we are describing here is just a very small language, right? So it has constants, it has variables which are strings, and the expressions are constants, variables. You have addition and multiplication, right? These are like subterms, right? These could be arbitrarily complex expressions. So that's the syntax, right? That is what we had seen in the previous class. Now we are looking at how do you describe the semantics, right? So, and the semantics, we provide semantics by writing an interpreter, essentially. So that's what we are going to do. And a short way of writing this is using this syntax. So these sort of brackets, right? The bracket with double bars here, they are known as Oxford brackets. I mean, there is an anecdote that is sitting behind this one, where the Oxford brackets came from. Actually, there's a nice paper. I mean, this is probably not interesting for non-programming language folks, but um, it's always called Oxford brackets. Everyone says it is Oxford brackets, but rarely do people realize that it does come from Oxford, but the origin of that Oxford bracket comes from a person from Stanford. So anyway, so if you're interested, I can share that paper. It's just a very fun exploration of how these concepts come up. See, the thing is, one thing to notice, right? So this is very close to mathematics. So these are all structures that people come up with, and oftentimes you have to come up with certain structures which did not exist previously. Humans did not know what those structures were, and you get the pleasure of naming these structures, and oftentimes they just stick on, and we just call this way of writing these brackets as Oxford brackets. And the way to read these term, right, when you have an n here and a v here, is that if you have an expression that you interpret in the context of some valuation v, a valuation is a map that maps from variables to natural numbers. If it is just a constant, then that has nothing to do, right? You just return the constant. If it is a variable, then the interpretation, right? The interpretation basically returns you a natural number. The interpretation of that variable is just lookup of that variable in the valuation. So whenever you see a v, you sort of imagine that to be the finite map that maps from variables to values. So for this term, which is e1 plus e2 interpreted under v, you interpret e1 under v, right, which gives you a natural number, and you interpret e2 under v, which gives you another natural number, and this plus, right, you sort of read this as just natural number addition. So this plus is part of the concrete syntax from the expression language here. This plus, you sort of say, okay, I am going to get a natural number here, 7. I'm going to get the natural number 3 here, say, and then the answer to this is 7 plus 3, right? That's the way to read this, and the same for multiplication, right? So you sort of interpret the subterms in the same valuation, and you return it. So the thing to note here is this language does not have a way of modifying or adding new bindings to this map, right? We just start with the static map, which has all the variables which are bound, and we sort of keep interpreting it without having a way to change it, right? So that's what we have in this very small language. And let's first explore up to this in the cockpit. Any questions on this so far?
Sir, in the previous slide
Yeah.
of MKV, so is it like we are writing K to V and also simultaneously reading the value at K?
So this one.
Any one of them.
So okay. So when you write this term,
Yeah.
right? It's just it's only saying that. So the way to read this is it is adding a binding kv to this map. So we're not reading it. So what you get as a result for this one is a map with this additional binding. So that is why it's called extension. So we are not reading k, we are adding. So if you want to think about very operationally, right? So the type of this would be, say, takes a map, right? Takes a key, takes a value, and returns you a new map. And the idea is that in this new map, if you ask what is the value of k, you'll get v, right? Which is what is being explained here. So if you take a map and then you extend it with kv, right? And you then look up what the value of k is, then you get v. So this itself returns you a map, right? This is this whole thing is just a map where for all the keys, right, which are not k, the binding still is the same. For the case where the key is this k, you have the binding which is v. Does that make sense?
Yes, sir.
It's just you can think of this as a function that returns a new map, right? And this is a strange way of writing this function. So it takes a map, it takes a key, it takes a value, and it's going to return a new map. We just like to write it this way because writing it in terms of functions just gets very tedious. Okay, so that's fine. So let's switch to the lecture slide. So again, we are going to import the Frap library. In addition to what we have seen in the slides, we are also adding a minus, right? So plus, times, and minus also with the usual meaning, right? And you can write the terms just as before. So this is all very standard. So here is the map, right? So this finite map. So this F map comes from Frap library. So you can check what F map is. It might have an interesting type. Yeah, it just says type to type, right? So it looks very, very generic, and it is supposed to be. So here's a cool thing about fmap, right? So typically when you write when you think about something like writing a map, by writing a hash table, say, let's just say you're writing a hash table in, say, your favorite programming language, say C++. You need a few things about the key, right? The first thing you need about the key is that if you use the red black tree as the storage, then you need a way to compare the keys, right? Given two keys, I need to get the answer for k1 less than k2, right? So it can either be equal or it can be less than or greater than. So there is this expectation, right? But this f map, right, doesn't say anything about the expectation here. It just says it's a type. It doesn't say that this type is something which you also need to be able to compare things on, right? So or in these advanced type systems, right? Equality is not for free. So not all types can be just compared by equality. You can't just say whether int equals bool. That just is a nonsense statement, right? So this fmap is quite cool because it doesn't expect you to show that this is a type on which you can do equality, or it is a type on which you can do comparison. I mean, of course, we are going to use strings here for which you can describe equality. You can also describe comparison function by lexicographic order, but that's not the point, right? This is a very generic map, and some details, it's okay if you don't get all of what I'm saying, but it's a nice construction. So it just works out for us. You don't have to do additional things on this map. So all we are saying here is that our valuation, right? Our valuation is this map, which is a map from variables to natural numbers, right? So that's what we are writing here. And the interpretation functions. So the thing that we saw here, right? This function is described as a recursive function. So what do we do here? We take the expression, we take the valuation, and we are going to return a natural number, right? In all of the cases. And that's precisely what this says, right? We are going to take an arithmetic expression, a valuation, and a natural number. And yeah, the const, the plus and times cases are fairly standard. This is exactly the same as what we described here. Minus is a little bit interesting because we do recursive interpretation, right? So we interpret E1, we interpret E2. It might be the case that E1 is 3 and E2 is 7, right? And because we are in natural number land, 3 minus 7 is going to be 0, right? So that's a thing to keep in the back of the mind. So we are not using integers, we are using natural numbers. So when you subtract 3 minus 7, it's going to stick at 0. This this is a fact that you need to keep in the back of the mind, because when you're proving things, right, you have to be cognizant of this fact. Let's keep it in the back of the mind. And the last thing that you want to do is, so what we say here is xv, and the value is just v of x, right? And the thing that we are assuming is that there is always a binding for x in v. If the valuation is empty, then this is not defined. But when you write programs, right, you actually have to describe a value. And there are a few things going on here. Let's go step by step, right? Oh, the variable is x, right? I need to look up the variable x in the map, right? So the syntax for that is dollar question mark, right? This is just the syntax that the Frap library chose. And the way to read this is, I am looking up the binding for x in v, right? What's the value? It returns an optional value. So if the binding is there, if it is some n, then I just return n, right? Which is what this meaning is, right? If there is no binding, I return this goofy default value. I say the value is 0. This is just a choice. This is not an informed choice, but it is sufficient for what we are trying to show in this lecture. This is a bit odd, right? So I might try to interpret what is the value of x plus 1 in an empty map. I will get 1 as the result, because of this choice, right? Because if you look up the variable x in this empty map, you'll get none. So you'll get 0 for that value. So that's a thing that we've done. That's just an aside. It's not going to bite us in what we want to do, right? So let's leave it at that. Any questions on this one? No, okay, fairly straightforward. Okay, and then so we said we have this map, right? And we had this way of taking an empty map and then extending it, right? We saw how to look up. Look up is through this dollar question mark. If you look up, you get an optional value back. We also need a way of extending the map with new bindings, right? And the way we do that is, okay, firstly, we need what an empty map is, right? How do you represent empty map? An empty map is just represented as $0. Again, this is a fairly choice which is very open, right? So it was just chosen as an empty map. And the way you extend it is using this dollar plus. So this extension syntax here is the same as this extension here. All you're saying is that this valuation 0 is has two bindings, right? One for x and one for y. When you look up x in valuation 0, you get 17. When you look up y, you get 3. Right? So we write it in this form. And if you keep extending this with x, right? Another binding for x here. This one shadows the inner one, right? So you're going outside here. So you keep looking at bindings from outside in. So if you want to if you want to simulate the fact that you are overwriting a particular binding, you just add one more binding. Right? If you can just do x 15 here, then if you look up x, you'll get 15. This has to be dollar plus. Right? So that's the way to read the syntax here. Okay. Yeah, okay. So questions on this one? I'll stop here, actually. I won't go further because we'll come back to what the implication of this map is. Questions? We're just scratching the surface. We'll look at the interesting properties and proofs and everything in the later lecture. After thing with Caucus, if you sort of understand the syntax, right, how it is organized, everything else sort of goes through fairly fine. Okay, if there are no more questions, we'll stop here and then we'll meet tomorrow. Right. Talk to you later. Bye.